This is a video for Physics 232C. This week we're studying Chapter 23, which is Modern Physics, and Chapter 24, which is Atomic Physics. Those two chapters sort of are combined to go together. Most students who've taken Physics 232 have had courses on chemistry. So some of this will be familiar to you. Chemistry is a science that explains how atoms are combined in molecules. For example, a chemical reaction is a rearrangement of atoms into different molecules. Atomic physics is concerned with the structure of the atom. So here's a sort of a picture of an atom. An atom has two parts. The nucleus, which is the positive charge at the center, and a cloud of electrons, which is the negative charge, which takes up most of the volume of the atom. The nucleus is very small compared to the atom itself, much smaller than in this picture. So most of the volume of an atom is the electron cloud. However, most of the mass of an atom is in the nucleus. The protons and neutrons that make up the nucleus have about the same mass, and they're both about 2,000 times more massive than a single electron. So, by far, most of the mass of the atom is at the center in the nucleus. But most of the size of the atom, or the volume, is in the electron cloud. So an atom, let's say an atom of the element with atomic number Z, would have Z protons and some number, N neutrons. That would make an isotope for that atomic number, and the mass Z plus N. And that would have charge plus Z times E. And then the electrons, well, in the neutral atom, there will be an equal number of electrons to the number of protons in the nucleus. So the charge, the complete charge of the electron cloud will be minus Z times E. So Z here, which is the atomic number, is on the one hand the number of protons in the nucleus, and on the other hand, it's also equal to the number of the electrons in the atom. N is the number of neutrons. For any given value of Z, there are several possibilities for N. So these would all have the same atomic number, but they would have different mass numbers. Those would be the different isotopes. And the mass of the atom would be, to a first approximation, just Z times a proton mass plus N times a neutron mass plus Z times an electron mass. And that would be a pretty good approximation for the mass of an atom. It's not quite accurate because there's some binding energy in the nucleus, and E equals mc squared, so if the energy is reduced by some amount of binding energy, then the mass is a little bit reduced. But that's usually small compared to the proton and neutron masses. All right, now the nuclear atom. So this is the first section of chapter 24. Goes back to Ernest Rutherford. Rutherford proved by an experiment that an atom has this form. There's the electron cloud, And of course, the electrons were known before Rutherford's experiments. The electrons were known from the experiments of J.J. Thomson. Thomson proved the negative charge comes from elementary particles, all identical, which we now call electrons. What Rutherford proved is that the positive charge is concentrated in a tiny center called the nucleus. So Rutherford's experiments were done over a period of a couple of years, but they sort of started in 1911. Now, how did he discover this? So the discovery of the atomic nucleus came from Rutherford scattering of alpha particles from atoms, specifically from gold atoms. So he had a target made of a thin foil of gold, and he shot into that target alpha particles. Rutherford was very familiar with alpha particles from the time when he lived in Canada. The alpha particle is the nucleus of a helium atom. To be precise, the isotope with mass number 4. So an alpha particle is 2 protons and 2 neutrons bound together by nuclear forces. It's very small, and there are various ways to obtain alpha particles, a beam of alpha particles to use in a scattering experiment. For example, some radioactive decays produce alpha particles. So alpha decay, which is something that Rutherford had studied earlier, produces alpha particles, and then since they're positively charged, this is not an atom, it's just the nucleus of an atom, so it's just the positive part of an atom. They can be accelerated by allowing them to pass through an electric field. And so you can have alpha particles, a beam of alpha particles with some variable energy that will be shot into the gold foil. Now, sometimes the alpha particle will come close to the atomic nucleus, and you can have this kind of scattering, where the alpha particle is coming in. Here's the gold nucleus. Forget about the electrons. The electrons are very lightweight, so they don't affect the motion of the alpha particle very much. I mean, Rutherford thought of the alpha particle as something heavy because it was much heavier than an electron. An alpha particle is about 8,000 times greater mass than an electron. So as the alpha particle comes through the electron cloud, it's not affected very much. But if it comes close to the nucleus, this tiny gold nucleus, it collides with an object with a large charge. The atomic number of gold is 79, so gold nucleus has a charge of 79 times the electron charge, or the proton charge, whereas the alpha particle is 2 times the electron charge, 2 times E, and very massive, much more massive than the alpha particle. The mass number, the most common isotope of gold, has mass number 197. Whereas the mass number of an alpha particle is only 4. So when this collision occurs, just think of it as a collision of 2 particles, which we studied back in Physics 231. The alpha particle will be deflected into some direction, and the gold nucleus will recoil a little bit. Because it's so massive, it doesn't change the energy of the alpha particle very much, but somewhat. A little bit of the alpha particle's energy is given to the gold nucleus as it recoils. And that's what Rutherford and his younger assistants observed. They observed occasionally an alpha particle scattered at a very large angle. This would be a scattering angle, maybe 80 degrees. Some alpha particles could even be scattered backwards. The alpha particle could even come back from the incident direction, because the gold nucleus is so massive. Think of it as a small bicycle. Well, no, bicycles would just crumple, but think of it as a small object colliding with a wall. It would just bounce back. And so Rutherford and his assistants even occasionally saw alpha particles bouncing backwards from their incident direction. And Rutherford immediately realized that that kind of large angle scattering is only possible if there's a massive center that the particle is scattering from. The electrons can't scatter the alpha particle backwards because compared to an electron, the alpha particle is very massive. Something can't bounce back from hitting something very light. It'll just continue going forward in a collision with an electron. Now, Rutherford was able to calculate the rate as a function of angle for scattering events, making the assumption that the gold nucleus, all of the mass is concentrated, and all the positive charge is concentrated at a scattering center, at the center of the nucleus. That's a calculation that can be done using classical mechanics, just a collision problem. And he could compare the count rate for backward scattered or sideways scattered at an angle theta, that rate compared to the angle. And he found perfect agreement. So his calculation, based on this picture and the mechanics of a collision between an object with mass 4 and an object with mass 197, where the force is 2e times 79e over r squared, the Coulomb force, based on the theory of the electric force and conservation of momentum, his calculation agreed perfectly with the experimental observations of the count rate as a function of scattering angle. So that showed that the atom has a nucleus. Now, following that discovery, Niels Bohr, famous Danish physicist, produced a model of the atom to try to calculate the energy in the atom, the energy of the electrons. And that's called the Bohr model. And if you've studied chemistry, I expect you've studied the Bohr model already. The Bohr model was developed by Niels Bohr about the same time as the discovery of the Rutherford form of the atom. That was not a difficult theory to develop. It's just based on the idea that an electron will be in an orbit around the nucleus. So you can do the calculation for the motion of the electron. It's just like a planetary calculation in astronomy. So this was not a difficult model to devise. But it had to account for the existence of atomic spectra. The fact that atoms don't radiate light of all frequencies. They only radiate light of certain discrete frequencies. That's called the spectrum. And that is not part of classical mechanics. So Bohr had classical mechanics to sort of describe the motion of an electron in a circular orbit, but he had to go something beyond that to include the fact that atomic energies are quantized. Well, this was, another early example of quantum mechanics. It became obsolete around 1927 after the idea of matter waves, first proposed by de Broglie, later put into an equation by Schrödinger. It turns out that if you go back in history, the Bohr model worked perfectly, well, very close to perfectly, for a hydrogen atom, one electron and one nucleus. But it could never be extended to atoms with many electrons. So it was successful in a limited way. The only real success of the Bohr model was applications to the hydrogen atom and to ions which have only one electron. All right, now you've probably studied the Bohr model in a chemistry class, but let me go over it here. We'll have hydrogen. Let's say a proton combined with an electron to make a hydrogen atom. And in classical mechanics, you would say the electron will be in some sort of an orbit. The most general case would be an elliptical orbit, just like planetary orbits in the solar system. But Bohr started with the simple idea that the orbit is a circle. So this is an example of circular motion. And classical mechanics tells you that, just Newton's second law, the mass times the acceleration is equal to the force. Well, we know the acceleration. The acceleration is v squared divided by r in circular motion. And we know the force. It's the Coulomb force. Two charges, charge E and minus E, have an attractive force equal to E squared over 4 pi epsilon 0 r squared from the very first chapter of this semester. So this would be one equation from classical mechanics. Now, Bohr postulated another equation which led to the success of the Bohr model. He postulated that angular momentum is quantized. In other words, angular momentum cannot take every value in a continuum. It can only take certain discrete values. So now let's look at what results. All right, angular momentum for an object in a circular orbit, for an object in circular motion, the electron in this case, is mass times velocity times r, the radius of the circle. L is mvr. And Bohr postulated that that quantity, MVR, is an integer multiple of some constant value, some smallest possible value. And in order to get the correct energy levels, the quantum has to be Planck's constant h divided by 2 pi. So here was Bohr's second postulate about the atom. L is h over 2 pi times n, where n is an integer. It could be 1, could be 2, could be 3, and so on, so on, so on. That's called quantization of angular momentum. Now, we'll see in a few minutes, that became obsolete after the wave theory of electrons was developed. But anyway, we're just studying Bohr's model for the moment. This quantity, h over 2 pi, appears in many places, so it's usually given a special symbol of its own. H over 2 pi is called h bar. It's h with a bar. So in many equations you'll see h bar. What is it? It's h over 2 pi. H divided by 2 pi. Planck's constant, which was known from the photon theory, divided by 2 pi. All right, so let's combine that with the equation of motion for circular motion. mv squared divided by r is equal to e squared over 4 pi epsilon 0 r squared. So this is mass times acceleration. This is the electric force, the force acting on the electron. We're sort of thinking of the proton as being at rest at the origin, and the electron goes around the proton on a circle. And that's a good approximation because the proton mass is so much larger than the electron mass. I mean, to be really accurate, you would say they both revolve around the center of mass point. But since the proton mass is so large compared to the electron mass, the center of mass point is almost the same as the center of the proton. So we just treat the proton as rest and the electron on a circular orbit. All right, so let's rewrite this equation. We have here m v squared over r. Well, let's cancel 1 power of r. So we'll say mv squared is e squared over 4 pi epsilon 0 r. We'll multiply both sides of this equation by r. So on the left-hand side, we'll just have mv squared. On the right-hand side, we'll have e squared over 4 pi epsilon 0 r. So here's the e squared over 4 pi epsilon 0 r. And now mv squared, well, from this equation, v is L over mr. So here's v squared, L over mr squared. All right, now L is h bar times n. So we'll put in here n h bar squared. We have here m divided by m squared, so that's 1 over m. We have here 1 over r squared. So you see I have an equation where the unknown is the radius of the orbit. M is the electron mass, h bar is Planck's constant divided by 2 pi, E is the electron charge, 4 pi epsilon 0, that's the electric force constant. Everything is known here except r. And it will depend on an integer, n, which can take any of these values. So let's solve for r. Multiply both sides of the equation by r squared. Then we'll have no powers of r here. We'll have r squared over r, 1 power of r over here. You see, r will be proportional to n squared. R will be some universal constant times n squared. And what is the universal constant? Well, it'll be h bar squared divided by m divided by e squared times 4 pi epsilon 0. We call that A0. A0 is 4 pi epsilon 0 h bar squared over m e squared. You see, it's just a combination of universal constants. Determine this radius. It's the quantum of the atomic radius. Well, not exactly. The radius goes like A0 times n squared. So the radius of this little electron orbit can be A0, that corresponds to n equal 1, or 4A0, that's n equal 2, or 9A0, that's n equals 3, 16A0. It's a constant A0 given by this combination of electron parameters, the mass and the charge, times a square integer, 1, 4, 9, 16, and so on. Now, this is A0 written in terms of known quantities, the mass of the electron, charge of the electron, and these epsilon 0 and h bar. If you plug in those numbers, you calculate the value of A0, it's 0.53 times 10 to the minus 10 meters. And that's called the Bohr radius. You see how classical mechanics and the Coulomb force lead to this dimension, 0.53 times 10 to the minus 10 meters. Now that's for hydrogen. For other atoms, you might expect this to be a little larger because there are many electrons. On the other hand, you might expect this to be a little smaller because the charge of the nucleus is larger and pulling the electrons in closer. So it's not obvious how this would depend on Z, the atomic number. But anyway, the order of magnitude is going to be something close to 10 to the minus 10 meters. So atomic radii are typically some number times the dimension 10 to the minus 10 meters. 10 to the minus 10 meters, or 1/10 of a nanometer, that's kind of a characteristic dimension for atoms. All right, so that's the radius of the electron orbit. Now let's go on and calculate the energy. All right, now, what are the energy levels of the hydrogen atom in the Bohr model? Well, let's suppose we have that quantum number n. That's really a quantum number coming from Bohr's postulate about angular momentum quantization. So n is an integer, 1, 2, 3, 4, etc. What's the energy of the electron in that circular orbit? Well, it's kinetic energy, a half mv squared, plus potential energy, minus e squared over 4 pi epsilon 0 r. This is the Coulomb potential energy for a charge plus E and a charge minus E. All right, now mv squared, remember mv squared divided by r was equal to E squared over 4 pi epsilon 0 r squared. So I can write this first term as 1/2 r mv squared over r. Well, now mv squared over r is the mass times acceleration, so that'll be equal to the Coulomb force, which will be E squared over 4 pi epsilon 0 r squared. The potential energy goes like 1 over r. The force goes like 1 over r squared. Now, you can cancel 1 power of r here, and you see both of these two terms are proportional to the same factor, E squared over 4 pi epsilon 0 r. This one times 1/2, this one times minus 1. So E will be minus 1/2 E squared over 4 pi epsilon 0 r. In other words, the kinetic energy on that orbit is 1/2 the magnitude of the potential energy. The energy itself will be negative. It'll be negative 1/2 E squared over 4 pi epsilon 0 r. So here's the E squared over 4 pi epsilon 0. Now I need 1 over r. But remember, r is a0 n squared. The quantization of the angular momentum in the Bohr model gives you definite Bohr radii a0 times n squared. So the energy levels are some constant divided by n squared. They're negative. So you have negative energies. That says the electron is bound to the proton, can't escape to far distances. And is proportional to 1 over n squared. And this constant proportionality we call the Rydberg, Ry, or the Rydberg constant, named for Swedish physicist Rydberg. Now, if we look at this combination, we can see what the Rydberg is. It's E squared over 8 pi epsilon 0 a0. Well, let's try to figure out what it is. It's let's see. How did I calculate this? Well, there's a factor of 1/2. Then it's E squared over 4 pi epsilon 0 a0. Now, a0 was 4 pi epsilon 0 over E squared, h bar squared over m. So 1 over a0 will be E squared over 4 pi epsilon 0. And then there'll be a additional factor of m over h bar squared. So I have 1/2 m over h bar squared, E squared over 4 pi epsilon 0 squared. So here we've written that Rydberg constant entirely in terms of electron parameters, the mass and charge of the electron. And if you plug in the values of the electron mass, electron charge, these fundamental constants, you find 13.6 electron volts. So in atomic physics, it's normal to measure energies in this electron volt unit. An electron volt is very small compared to a joule, which would be the standard unit of energy. So we just it makes more sense to use a unit which is kind of the right order of magnitude. So instead of using joules, we'll use electron volts. The electron volt is 1.602 times 10 to the minus 19 joules. It's just 1 electron charge times 1 volt is the electron volt. It's the energy picked up by an electron if it moves through a distance of 1 volt, through a potential of 1 volt. Now the electron charge is 1.602 times 10 to the minus 19 coulombs. So this is 1.6 times 10 to the minus 19 coulombs times 1 volt. So to convert from electron volts to joules, because a coulomb times a volt is a joule. That's a standard unit. So to convert from electron volts to joules, we just have this factor equal to the electron charge in coulombs. All right, so the energy level of the orbit with quantum number n is minus 13.6 electron volts divided by n squared. So we can make a little energy level diagram here. So here's an energy axis. And we'll, normally writing those energies in terms of electron volts. Well, the lowest energy state, we call that the ground state, has n equals 1. So then E sub n is minus 13.6 electron volts. So down here at, well, I have it over here, minus 13.6 electron volts, that's the orbit with n equals 1. That's the lowest energy state. A hydrogen atom cannot have an energy less than negative 13.6 electron volts. That's the lowest possible energy. The hydrogen atom can't have energy. It can't have any energy along this energy line. It can only have certain discrete values. For n equals 1, the value is minus 13.6 electron volts. For n equals 2, it'll be minus 13.6 divided by 4 electron volts. That's minus 3.4 electron volts. For n equals 3, it'll be minus 13.6 electron volts divided by 9. That's minus 1.51 electron volts. So, according to the Bohr model of the atom, these are the possible energies of an atom, of a hydrogen atom. And this turns out to be quite accurate. Although the Bohr model became obsolete when the wave theory of electrons was developed some years later, but until that time, and that was, about 15 years later, the Bohr model was the best theory for the energy levels of atoms, and it turns out to be quite accurate for hydrogen. And for ions in which there's only one electron. Now, for an ion with charge Z and one electron, the energy level would be this E sub n, E sub 0, no, E sub n would be minus 13.6. Let's just write 14 over n squared. Times z squared. So I guess I have to make a little space here. Times z squared. So suppose you had not hydrogen, but once ionized helium. A helium atom with one electron removed is a nucleus with charge 2e and one electron. So Z would then be 2. And the lowest energy level here would be minus 13.6 times 4, Z squared. So there will be some problems on the Lon Kappa assignment where you'll deal with one electron ions. And then the energy levels are a hydrogenic energy level times Z squared. You can see why it's Z squared. It's because instead of E squared here, I would have ZE squared in going from hydrogen to, let's say, helium plus, once ionized helium. I would have an additional factor of Z, but that quantity becomes squared. So the Rydberg would be, well, the Rydberg's always 13.6 electron volts, but the quantity down here would be the additional factor of Z squared. Anyway, you'll find this discussed in the book, and anyway, you have to do this for some of the Lon Kappa problems. All right, so the spectrum of atomic hydrogen, and also for one electron ions, is accurately described by the Bohr model. We have these energies, minus 13.6 electron volts, minus 3.4 electron volts, minus 1.51 electron volts, and so on and so on and so on. As n increases, the energy level approaches zero from the negative side. So we have an energy level diagram here. We can draw a diagram showing the energy levels. And now, when the atom is in an excited state, it can emit a photon and make a transition to a lower state. You know, the hydrogen atom must have one of these. I've only drawn 4 of them, but the hydrogen atom must have one of these 4 values of energy. If it's in, let's say, the n equal 2 energy level, it can make a quantum jump to n equals 1, but energy must be conserved, so it has to emit a photon. And that's the most common kind of atomic transition. Transition from an excited state to a lower state with the emission of one single photon. Energy is conserved, so the energy of that photon will be the energy of the upper state minus the energy of the lower state. So E sub n minus E sub n prime will be the photon energy for a transition from n to n prime, where n is greater than n prime. So for example, I might have n equals 2 to n equals 1. So n would be 2, n prime would be 1. I'd have here minus 1 over 4 plus 1 over 1. So this is 3/4 times a Rydberg. So this photon, for a transition where the atom goes from the n equal 2 energy level to the n equal 1 energy level, would have energy 3/4 times a Rydberg. And again, as I say, if instead of hydrogen you had a 1 electron ion, you would multiply by Z. No, Z squared. You multiply by Z squared because the energy levels are minus 13.6 over n squared times Z squared. All right, so that gives you certain wavelengths. I can have a wavelength where the energy is minus 1 over n squared plus 1 over n prime squared, where those are both integers, times a Rydberg. Let's express it in terms of the wavelength, though. Remember, wavelength is speed of the wave divided by frequency. So that's the speed of light. We're talking about light being emitted, so a photon. Wavelength is c over f. Multiply numerator and denominator by h, Planck's constant. That's hc over hf. hf is the photon energy. So you see, the energy of the photon is hc divided by lambda. So I could write this as 1 over lambda divide by hc on both sides of the equation. 1 over lambda is the Rydberg divided by hc, 1 over n prime squared minus 1 over n squared. And n and n prime here have to be integers. 1, 2, 3, 4, and so on. That was known before the Bohr model. That's called Balmer's formula. So Balmer was a scientist who measured atomic spectra. And he noticed that the atomic spectrum of hydrogen could be described by this formula. The discrete values of the wavelength are some constant times 1 over an integer squared minus 1 over another integer squared. So, again, the Bohr model gave certain discrete energy levels, implying certain photon wavelengths. And that agreed with the experimental values for the photon wavelengths, the colors of the light that had been discovered earlier in the study of atomic spectra by people like Balmer. So all of these transitions have different names associated with them. I think I have these numbers wrong, but there's the Lyman series where n prime is equal to 1. So it can make a transition from n equals 2 to n prime equals 1, or n equals 3 to n prime equals 1, or n equals 4 to n prime equals 1. We'll have these values for the energy, these values for the wavelength. So that's called the Lyman series. Some of these I think are all ultraviolet. So these correspond to ultraviolet wavelengths. There are the transitions where the final value of n is 2. So you can have a transition from n equals 3 to n equals 2, or from n equals 4 to n equals 2, or from n equals 5 to n equals 2, or n equals 6 to n equals 2. In other words, there are an infinite number of transitions where the final value is 2, where n prime is equal to 2. That's called the Balmer series. These are visible. So if you do a spectral analysis of hydrogen, you'll find a bunch of different spectral wavelengths which are in the visible range of light. Finally, here's another series where the final energy level is n equals 3, or I should say n prime equals 3. So you can have the transition from n equals 4 to n equals 3, or n equals 5 to 3, or 6 to 3, and so on and so on. That's called the Paschen series, and these are infrared. So these transitions have high energy. They correspond to ultraviolet wavelengths. These transitions have kind of middle-sized energy. They correspond to visible wavelengths. And then these higher transitions are infrared transitions. But there were spectrometers that could observe all of these different wavelengths. Okay then, the Bohr model was successful in describing the energy levels and the corresponding atomic spectrum of hydrogen. So that looked like a great success. However, the Schrodinger equation, developed in 1927, made the Bohr model obsolete. In fact, the Bohr model really was never successful for anything except hydrogen or one electron ions, whereas the Schrodinger equation could be applied to atoms with multiple electrons. Now, the Schrodinger equation describes the electron as a wave, and the Schrodinger equation has multiple quantum numbers. The Bohr model describes the electron as just a particle moving around on a circle. But the Schrodinger equation, so the Bohr model only has one quantum number, n, which is related to both angular momentum and energy. But the Schrodinger equation is more complicated because in the Schrodinger equation, the electron is a wave. So in fact, there are, three quantum numbers plus one additional quantum number having to do with electron spin. So the electron states in a hydrogen atom actually have four quantum numbers: N, L, M sub L, M sub S. N is called the principal quantum number. The allowed values of N are 1, 2, 3, 4, and so on, just positive integers. And the energy of any state with principal quantum number N is minus 13.6 electron volts divided by N squared. Now you see that is consistent with the energy levels in the Bohr model. But in the Schrodinger equation, there are also angular momentum quantum numbers. So L is called the total angular momentum quantum number. And the allowed values of L are 0, 1, 2, 3, 4, so on, up to n minus 1. They're all integers. They're not all possible integers. They start at 0 and they end at n minus 1, where n is the principal quantum number. So if n is equal to 1, then the only possible L value is 0. And that's called the 1s state. If n is equal to 2, L could be either 0 or 1. And that's called the 2s state and the 2p states. And if n is equal to 3, L could be 0, 1, or 2. And those are the 3s states, the 3p states, the 3d states. And if n is equal to 4, there are the possible values of L, 0, 1, 2, 3. 4s, 4p, 4d, 4f. So n, the principal quantum number, is related to the energy. L is related to angular momentum, and it depends on how large n is. The angular momentum quantum numbers, L is the total quantum number, M sub L is the z component of angular momentum, M sub S is the z component of spin. L squared is h bar squared L plus 1. See, it's a little bit different than in the Bohr model. In the Bohr model, Bohr assumed that L is h bar times n. Well, in the Schrodinger equation, treating the electron as a wave, L is h bar times the square root of LL plus 1. And L, well, there are various possibilities. So L equals 0 is called S states. L equals 1 is called P states. L equals 2 is called D states. L equals 3 is called F states, and so on. Now there are these two additional quantum numbers, M sub L and M sub S. The Z component of L is H bar M sub L. So in the Schrodinger equation, you have to decide on some direction to define as the Z direction, and then the Z component of orbital angular momentum is quantized in units of H bar. It's reminiscent of the Bohr model, but it's more complicated. And what are the possible values of L, M sub L? Well, they depend on L, the total orbital angular momentum quantum number. So M sub L could be 0, plus or minus 1, plus or minus 2, and so on, up to plus or minus L. You can't have Z component of L greater than the total angular momentum. So it sort of stops at L. It could be pointing either upward or downward, so it could be plus or minus L. And then all the integers down to 0. So for a given value of L, there are 2L plus 1 values of M sub L. So the S states have only one possible value of M sub L, namely 0. But the P states have three possible values of M sub L, 0, plus or minus 1. And the D states have 5 possible states, 0, plus minus 1, plus minus 2. So the two P states are actually 3 states because of the 3 different values of M sub L. And the 3 D states are really 5 states because of the 5 different values of M sub L. Now, there's another kind of angular momentum intrinsic to the electron. This is orbital angular momentum. That's the angular momentum associated with the motion of the electron in space. But internal to the electron, there's an angular momentum called spin. And again, it's quantized in units of h bar. The Z component of the spin can be h bar times M sub S, and M sub S only has 2 values, plus a half or minus a half. So you can have a spin up electron, which has S sub E as h bar over 2, or you can have a spin down electron, which has S sub Z is minus h bar over 2. So actually, if you're counting the number of states, suppose you have principal quantum number n, total orbital angular momentum quantum number L, how many possible electron states are there? Well, the number of distinct states with these two quantum numbers are 2L plus 1 from the different values of M sub L, 2L plus 1, times 2, because there are 2 possible spin states. So times 2. So this gives you same energy levels as in the hydrogen atom, as in the Bohr model, but a different counting of the number of states. Because in the Bohr model, there would only be one state with n equal 1 and one state with n equals 2, corresponding to, one circle for each value of n, one circular orbit. So it's quite different because a wave has more degrees of freedom than just a particle on a circle. So even in the wave theory, angular momentum is conserved, but it's just that the quantum numbers are more complicated. Angular momentum is conserved, it's quantized, but it's quantized by two quantum numbers, and even a third quantum number if you count the spin angular momentum. Now, if you've studied chemistry, you've probably seen the answer to this question, but this raises a question for all these different kinds of states. What does an electron wave look like? Here's the Bohr model. An electron state is a particle moving around a circle. That's not a wave. That's a particle. But the electron states in a hydrogen atom are really wave states. So what do these electron waves look like? If you've taken chemistry, you probably already know this, but let me show. Well, here's a picture taken from the internet, which shows hydrogen atoms' wave functions. So a hydrogen atom has one electron, and these standing waves describe the electron in a hydrogen atom. There are many different states. There are states with n equals 1 and L equals 0. The electron is a little standing wave in a spherically symmetric form. Here's the case where n is equal to 2, L is equal to 0. It's again spherically symmetric, but it has a node. It has a region where the wave function is 0. So it has a peak in the center, and then a region where the wave function is 0, and then another peak, well, actually a trough, making a spherical wave, a spherical standing wave. Here's the case for n equals 3, principal quantum number 3, L equals 0. So again, it's spherically symmetric. It's a spherically symmetric wave, but it has two nodes. There are two radii where the electron wave function is 0. So, it has a peak followed by a node, followed by a trough, followed by another node, followed by another peak. And it's spherically symmetric. Now, what about cases with L equals 1? Well, L equals 1 cannot have n equals 1. L equals 1 means n has to be 2 or larger. So here's n equals 2, L equals 1. It's no longer spherically symmetric. It has a kind of a shape. It has a kind of a dipole shape. This corresponds to one of the values of m sub L. This corresponds to m sub L equals 0. But there are also waves with m sub L equals plus 1 and m sub L equals minus 1, which have their nodal shapes are sort of orthogonal to this. Or here's n equals 3 and L equals 1. It's again got this dipole shape, and two other shapes which are sort of orthogonal to this, where there are additional regions where the wave function is 0. So they're standing waves. And here's n equals 3, but L equals 2. Now it's more of a quadrupole shape. It has sort of 4 poles and a more complicated nodal structure, the nodes being the regions where the wave function is 0. So here's, I guess it says positive values of the wave function are yellow and red. Negative ones are cyan and blue. So, over on this side, which is the xy plane, you have a region where there's a wave function. And in the z direction, you also have a region. So you have sort of like 4 regions where the wave function is not 0. Well, if you've taken a course in chemistry, you've probably seen pictures like this. And, N can continue on to N equals 3, N equals 4, N equals 5. L can continue, L equals 0, 1, 2, 3, and so on. But always the maximum value of L is N minus 1. So here's N equals 1, L equals 0, N equals 2, L equals 1, N equals 3, L equals 2. So these are the cases where the angular momentum quantum number is the maximum possible. All right, so these are sort of solutions, these are sort of visualizations of solutions for the Schrodinger wave function. The great success of the Schrodinger theory of the electron waves was that it explains the periodic table of the elements. The periodic table was first determined from chemistry by Mendeleev. Then it was explained by atomic physics from quantum numbers and the Pauli exclusion principle. So this is a sort of an empirical determination of the elements ranked by atomic number, and atomic physics provided the theory. Quantum mechanics, the Schrodinger electron waves, explained it. The Pauli exclusion principle says that given specific values for the 4 quantum numbers, at most one electron can have these values. And so, for example, with n equals 1, L equals 0, m sub L has to be 0, m sub S could be plus or minus a half. 2 electrons can go in the n equal 1 level. So, for example, in the helium atom would have 2 electrons in the 1s state. For n equals 2, you can have L equals 0 or 1. L equals 0 has only 1 m sub L value, but L equals 1 has 3 m sub L values. So there are really 4 states with n equals 2. Times 2 for those 2 spin states gives me 8 particles that can go into those 8 states, plus the 2 that went into the n equal 1 level. That means you can put 10 electrons in the energy levels n equals 1 and n equals 2. That corresponds to neon. Neon has atomic number 10. It's 2 1s electrons, 2 2s electrons, and 6 2p electrons, making 10. And similarly, with n equals 3, you can have L equals 0, 1, 2. L equals 0 has 1 m state. L equals 1 has 3. L equals 2 has 5. Altogether, multiplied by 2 for the 2 spin states, there can be 18 different states with n equals 3. So the energy levels get a little bit mixed up when you have multiple electrons, because the electron-electron interactions affect the energy. But we can identify filled shells with the noble gases, and they will have quantum numbers given from this little table. So, for example, helium has 2 electrons, neon has 10 electrons, argon has 18 electrons. It's got the 10 electrons for neon plus 8 more. Gives me 18. Then if you add the additional n equals 3 electrons, you can have krypton with 36, atomic number 36. So, the noble gases, helium, neon, argon, krypton, xenon, radon, correspond to atomic numbers 2, 10, 18, 36, 54, 86, which correspond to filled combinations of the energy levels with n equals 1, 2, 3, 4, and various values of L. So you get these electron configurations. For example, oxygen has Z equals 8. It's not a noble gas. It's highly chemically reactive. But how do you create an atom with 8 electrons? Well, there can be 2 in the 1s state, 2 in the 2s state, 4 in the 2p state. That gives you altogether 8 electrons. So that gives me the electron configuration for the ground state of oxygen. If you've studied chemistry, you've seen the periodic table of the elements. So this shows all the elements with their corresponding atomic numbers: hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. These are the noble gases where you have filled shells: helium, neon, argon, krypton, xenon, radon. And then each column corresponds to some other combination of electron configurations. So here's again the periodic table of the elements, but now showing not the element name, but the electron configuration, showing the last orbital filled for each element. So hydrogen, 1s1. Helium, 1s2. Lithium, 2s1. Beryllium, 2s2. Where's oxygen? Oxygen, 2p4. Where's neon? 2p6. So it's got atomic number 10. 2 electrons in helium-like orbitals and 6, well, plus 2 in S states plus 6 in P states gives me altogether atomic number 10. So the periodic table, determined empirically by chemical properties by Mendeleev, was explained by quantum mechanics, by the Schrödinger theory of electron waves. Okay, so atomic physics, Schrödinger's theory of electron waves, and the Pauli exclusion principle explain the periodic table of the elements. Now there's one final section in chapter 24, section 5, which concerns X-rays radiated by atoms. This can happen when a high-energy electron hits an atom. So imagine an experiment like this. You have an atom, which contains many electrons, and you have a high-energy electron, which is shot into the atom. So this is, an X-ray. In other words, it's a very high energy. That electron can knock one of the electrons in the atom out, leaving a space in the set of electron orbitals for the atom. Then there can be a transition, a quantum jump, from one of the other electrons in the atom down into that empty space. If that empty space is at a low energy. It's an electron orbital close to the nucleus. Well, that will produce electromagnetic waves that transition from a higher atomic state to a lower atomic state. The intensity as a function of wavelength for the X-rays emitted by the atom has a continuum part, and that's the process called Bremsstrahlung. And the interesting fact there is there's a minimum wavelength that can be produced. Remember, low wavelengths correspond to high energies, high frequencies. So it's kind of a maximum frequency that can be produced by Bremsstrahlung. But then there are also some peaks in the intensity distribution. These are called characteristic X-rays. So the Bremsstrahlung is sort of common to all the atoms, but the peaks are peculiar to the individual atoms. They're different for different atoms. There are multiple X-ray peaks. In the book, they'll explain there's a group called the K-alpha wavelength and the K-beta wavelength. And then there is also another group called the L-alpha and L-beta wavelength. So there are a number of wavelengths of X-rays produced by an atom. The minimum wavelength, which is to say the highest energy photon, is determined by the energy of this incoming electron, which is colliding with the atom. So this electron brings in with it, oops, I shouldn't call that X, it's not an X-ray, it's an electron. So this incoming electron has a certain energy. Let's call that E sub E. And say that's given. So, over here we have some kind of electron gun. And it produces electrons which then collide with an atom. So E sub E is determined by the electric field in the electron gun. Well, that's the maximum amount of energy that you're going to be able to get out in the form of an X-ray. So E gamma, we use gamma for photon, the maximum photon energy will be that electron energy. You can't get more energy out than you put in. Now remember, wavelength is C over frequency, multiply numerator and denominator by H, that's Hc over photon energy. So the minimum wavelength of the X-ray produced will be the maximum photon energy. That corresponds to the electron energy of the incident electron. Hc has a value 1,240 electron volt nanometers. The electron energy is one electron charge times the voltage of the electron gun. So we can write this as 1,240 volt nanometers divided by the voltage of the electron gun. So this is explained in section 5, and there'll be a homework problem which involves that. But what's more interesting are the characteristic X-ray peaks. The characteristic X-ray wavelengths. And this was studied by Moseley, Henry Moseley, in 1913. He was doing these experiments and observing the wavelengths of the X-rays produced. After the collision, there'll be an outgoing X-ray, and he could measure those X-ray wavelengths. And plot the intensity as a function of the wavelength. He found these peaks. And Moseley determined that the frequency is proportional to the atomic number of the atom squared, or the square root of the frequency is proportional to the atomic number. That's called Moseley's law. The book gives actually a more accurate relationship. The square root of the frequency is actually proportional to z minus 1 squared. But if z is large, then the difference between z and z minus 1 is a minor thing. So Moseley said square root of f is proportional to z, and explained it from the Bohr model. Remember, the energy levels in the Bohr model go like z squared? Those are for the energy levels of orbitals close to the nucleus, the inner orbitals. So these come from electron transitions involving orbitals near the nucleus, where the faraway electrons are sort of irrelevant. And since it only involves one or maybe a few inner electrons, the Bohr model should describe it pretty well. I mean, the Bohr model works very well for hydrogen, one electron. So, the K alpha X-ray corresponds to a transition to a 1s state. K beta is a transition to a 2s state, and so on. So using that Bohr model energy level diagram, Moseley could derive a relationship between the wavelength produced in that transition and the atomic number. It involves the Rydberg energy and the atomic number, Z. So this is sort of explained in a little more detail in the book, and there'll be a line kappa problem involving Moseley's law. Moseley was just a very young man at the time, and 1913, so this was just after the Bohr model had been developed, just after within a year or two after the Bohr model had been developed, a year or two after the Rutherford model of the atom, the nuclear model, had been developed. And Moseley was a very young man. And this was at the time of, close to the beginning of the First World War. The First World War started in 1914. Moseley, being a young man, enlisted in the British Army as an engineer, and he was killed in one of the earliest battles in the First World War, the Battle of Gallipoli, where Britain and the British allies were fighting against the Turkish Empire. Gallipoli is a region in Turkey. Hundreds of thousands of soldiers were killed in that Battle of Gallipoli over a period of about 6 months. One of the first big battles in the First World War. And Moseley died in that. People said that he would have gotten the Nobel Prize if he hadn't been killed in the First World War. Because really these experiments proved the Rutherford model. These experiments, along with the Bohr model, proved that Rutherford's model for the atom, a nucleus surrounded by electrons in different orbitals, is a correct description of the atom. All right, so this week we're studying chapters 23 and 24. The Lon Kappa assignment will be somewhat long this week because it involves two different subjects, but you should be able to now go read those two chapters in the textbook and then do the Lon Kappa problems.